When massive cosmic bodies like neutron stars or black holes collide, huge amounts of mass are converted into pure energy. That violent process emits tiny ripples in spacetime that travel outward in every direction. Sometimes these gravitational waves eventually reach Earth. We detect them using highly sensitive ground-based laser interferometers, like the LIGO observatory seen here. This graph illustrates the standard signature we expect from two merging black holes. It happens in three distinct phases: the inspiral, the merger at the absolute peak, and the ringdown. During the inspiral phase, the black holes circle each other faster and faster, radiating away energy. The wave's frequency and amplitude increase over time, creating a rising chirp. In May 2019, a signal designated GW190521 washed over our detectors. Researchers initially interpreted it as the historic first observation of an intermediate mass black hole, but this chart shows a direct comparison of the expected waveform against what we actually recorded. The GW190521 signal is completely missing the inspiral phase. It lasts a mere tenth of a second, showing only the merger and the fading ringdown. A gravitational wave without an inspiral phase defies the established models of binary black hole collisions. The missing data presented an immediate problem for the scientific community, leaving researchers struggling to explain how a massive collision could seemingly begin halfway through. In 2025, a research team led by Qi Li at the Hangzhou Institute for Advanced Study examined the missing waveform, proposing an entirely different mechanism. They suggested the collision didn't happen in our reality at all. In this model, our universe sits on a bottom plane, and a parallel universe sits on top. Up there, two black holes spiral together and merge normally. Instead of forming a single larger mass, the collision punched a hole through space-time. The inspiral stayed in the parallel universe, but the resulting tunnel allowed the final ring-down ripples to bleed through into ours. Evaluating an inter-universal signal requires subjecting the theory to the same strict relativistic physics we apply to black holes. The theoretical foundation for these structures comes from Albert Einstein. His field equations naturally produce a geometric solution where a black hole connects to its exact opposite, a white hole, forming a theoretical bridge. The mathematics also reveal a severe structural flaw. An Einstein-Rosen bridge is inherently unstable. The crushing gravity causes the throat to collapse so instantly that absolutely nothing, not even a beam of light, could cross it. In 1988, astrophysicist Kip Thorne and his colleague Michael Morris outlined a mathematical method to hold these collapsing tunnels open. They proposed lining the throat with a theoretical substance called exotic matter. Unlike standard matter, exotic matter possesses negative mass and negative energy density, giving it highly unusual physical properties. This diagram shows how that exotic matter would function. While normal matter attracts everything around it, negative energy does the exact opposite. It repels. That outward pushing force acts as scaffolding, counteracting the extreme gravity trying to crush the tunnel. While the math allows negative energy to maintain the physical geometry of a tunnel, keeping the door open doesn't explain how complex data like a gravitational wave could travel through it without being scrambled into static. General relativity explains large-scale gravity, while quantum mechanics dictates subatomic behavior. When we try to apply both sets of rules to a black hole simultaneously, the math contradicts itself entirely, creating what physicists call the firewall paradox. In 1974, Stephen Hawking demonstrated that black holes are not completely dark. They experience quantum effects near their edges, causing them to slowly leak radiation and evaporate over immense periods of time. A 2013 hypothesis known as the ER EPR conjecture suggests a way to unite Hawking's quantum radiation with Einstein's geometric gravity. In quantum mechanics, when two particles become entangled, their states are permanently linked. If you measure the spin of one particle, its partner instantly snaps into the opposite spin, even if separated by billions of light years. The ER equals EPR conjecture argues that this instantaneous link isn't magic. It suggests that every pair of entangled particles is physically tethered together by a microscopic Einstein-Rosen bridge connecting them across spacetime. If the Hawking radiation escaping a black hole is entangled with the particles trapped inside, those tiny threads provide a physical path. The information carried by the engulfed matter is preserved and remains connected to the outside universe. If this conjecture holds, wormholes represent more than just transit tubes. They are the geometric scaffolding that might finally link quantum mechanics and gravity together. In 2022, a team at Caltech tested this relationship using a superconducting quantum processor to create a virtual holographic wormhole. They set up two entangled quantum systems. The researchers injected a unit of information into the first system and then applied a specific rotation to the particles, mathematically simulating a pulse of negative energy holding a tunnel open. The information successfully passed out of the first system and reconstituted itself in the second. By following the strict rules of quantum entanglement, the computer accurately simulated data traveling through a gravitational wormhole. However, the Caltech test represented a pristine, perfectly balanced system. In 2025, another team built a mathematical model to see if an Einstein-Rosen bridge can survive the chaotic, violently fluctuating environment of an actual black hole. They actively scrambled the quantum entanglement, simulating extreme physical chaos, but instead of collapsing, the geometric structure held. The simulated tunnel grew longer and highly deformed, earning it the name Einstein-Rosen caterpillar, but it remained a stable, traversable path. These simulations and models indicate that a traversable tunnel is a mathematically sound concept, even when subjected to the chaotic conditions of a real black hole. We can now apply this established physics back to the missing waveform of GW190521. If negative energy can hold a throat open, and a messy quantum structure can successfully transmit data, a leaked ring-down from a parallel universe fits within the boundaries of physics. The authors of the 2025 study concede that despite the missing in-spiral phase, a highly unusual binary black hole collision within our own universe still aligns slightly closer with the recorded data. But confirming an alternate universe was never the sole purpose of the research. The study successfully establishes a concrete mathematical framework, allowing astronomers to test highly theoretical physics directly against real physical detector data. The precision of that data is constantly improving. Since late 2023, both the LIGO and Virgo observatories have operated with a 30% increase in base sensitivity. Our detectors are no longer restricted to cataloging the predictable collisions of standard stellar masses. We have the capability to monitor the sky for anomalies that exist precisely at the intersection of microscopic quantum mechanics and vast gravitational structures. The investigation into GW190521 shows that while wormholes remain elusive, they are moving from abstract equations into the realm of testable physics, offering a new methodology for interpreting the most mysterious signals in our sky.